Welcome to SRK Masterstack. Today we're diving into something that's transforming how AI agents work in the real world. It's called harness engineering. Andrew, what exactly is this all about?
Great question, Jenny. Harness engineering is the discipline of building the infrastructure around AI models that makes them reliable in production. It's everything between the user's request and the model's response that isn't the model itself. Context assembly, tool orchestration, verification loops, and monitoring.
So it's like we're building a cockpit for the AI pilot? Give me a good analogy.
Exactly that. Imagine a highly skilled pilot alone in the sky with no instruments, no checklists, no air traffic control. They would crash eventually. The model is the pilot. The harness is the cockpit instruments, the checklists, the alarms, and the autopilot. The pilot has the skill, but the cockpit makes flying safe and reliable.
When did this become an actual named discipline? It feels brand new.
Early 2026. Two things happened. First, OpenAI published how they build internal agent infrastructure, describing guides and sensors. Then Mitchell Hashimoto, creator of Terraform, distilled it into one formula: agent equals model plus harness. That formula became the foundation of the field almost overnight.
And why does this matter? How big of a deal is it really?
Huge. Without a harness, AI models fail up to 30% of the time on complex tasks. 27% of agent failures trace to bad data, not bad models. And here's the key finding. Swapping to a better model improves quality by maybe 10 to 15%. But improving the harness improves quality by up to 80%. The harness is where reliability lives.
Let's dig into that formula. Agent equals model plus harness. What does each piece actually do?
The model is the intelligence engine. It reads text, reasons through problems, generates responses, and decides which tools to call. But a model alone is like a brilliant junior employee with no manager, no documentation, and no processes. The harness is everything else. It tells the model what its job is through system prompts. It provides context from knowledge bases. It gives tools like search, calculators, and file access. It also checks outputs before they reach users, catches hallucinations, tracks costs, and logs everything for debugging. The harness transforms raw model capability into reliable production behavior.
So the model provides raw intelligence, but the harness decides whether that intelligence is actually useful in practice.
Exactly. There's a formula for this too. Production capability equals model capability times harness quality times environment quality. All three matter, but the harness is the lever we can actually engineer.
So what actually goes into a harness? Is there a mental model for thinking about the components?
Yes. Software architect Martin Fowler gave us a brilliant taxonomy. Everything in a harness falls into two categories: guides and sensors. Guides are feed-forward controls. They tell the agent what to do before it acts. Sensors are feedback controls. They check what the agent did after it acts. You need both.
Give me concrete examples of each. Let's start with guides.
Guides include system prompts that set the agent's role and rules. Agents.md files with project-specific guidance, constraint documents that define permitted actions, and context pipelines that supply relevant data from knowledge bases or databases. Think of them as the recipe before you start cooking.
And sensors?
Sensors include evals that score output quality, validation loops that check outputs before sending them to users, output parsers that extract structured data from model responses, drift monitors that detect if quality degrades over time, and cost trackers that alert if a query costs too much. Think of sensors as the quality control inspector after production.
So guides prevent mistakes, sensors catch the ones that slip through. You need both for a complete system.
Exactly. A harness with only guides is wishful thinking. A harness with only sensors is always reacting to failures after they happen. The full loop is guides direct, the agent acts, sensors verify, and that feedback improves the guides. That's the harness cycle.
Not all harnesses are equal though. I've heard about the H0 to H3 maturity ladder. What does that look like?
The H0 to H3 ladder describes 4 levels of harness maturity. H0 is raw model, no harness. Think of a basic chat interface. Type a question, get an answer. No system prompt, no tools, no verification. It's useful for simple chats, but completely unreliable for anything important. Most public AI chatbots are at H0.
What about H1?
H1 adds basic instructions. A system prompt, maybe a simple tool like a FAQ search. This is where most customer service chatbots live. But the model can still hallucinate product details or ignore policies because there's no verification step. It's better than nothing, but still risky.
H2 sounds where things get serious.
H2 is the sweet spot for most production systems. Structured prompts, multiple tools, context from databases, output validation, and full observability with logs and traces. A coding assistant that can read your files, run your tests, and check its own work before suggesting code is an H2 system. Most problems are caught before they reach the user.
And H3? That's the holy grail?
H3 is full production grade. It adds deterministic verification where specific requirements must be proven met. Complete audit trails for regulatory compliance. Entropy monitoring that detects when the model is uncertain. And human-in-the-loop oversight for critical decisions. These systems go into hospitals, banks, and airlines. Every action is logged. Every decision is reviewable, and nothing slips through.
Where are most real-world systems today?
Most are at H0 or H1. A few advanced teams have reached H2. H3 is still rare and mostly in highly regulated industries. The goal of harness engineering is to make H2 and H3 accessible to everyone building AI agents.
Let's get practical. If I wanted to build a minimal harness for a customer support bot, what would that look like? Walk me through it step by step.
Step 1. Write a clear system prompt. Define the agent's role and rules. You are a support agent for Acme Corp. Be polite. Never make up facts. If you don't know, say you don't know. That's your first guide. Step 2. Build a context pipeline that gathers relevant information for each request. Order history, product catalog, FAQ articles. Step 3. Define tools. Let the agent look up orders by ID, check product inventory, and escalate to a human agent when needed. Each tool has a clear name, description, and input parameters. Step 4. Add sensors. Validate every output before it reaches the customer. Does the answer match our catalog? Is the tone appropriate? Is customer data protected? Step 5. Log everything. When something goes wrong, you need the full picture. What was the question? What context did the model receive? What did it answer? Why did it fail? This turns every mistake into a learning opportunity and a permanent improvement to your system.
So the golden rule is, never trust the model blindly, always verify, and always learn from failures.
Exactly. Schema-based validation after every tool call is the minimum viable harness. And don't try to build everything at once. Week 1, write a system prompt and 1 validator. Week 2, add a knowledge base. Month 2, start tracking metrics. Build incrementally.
What are the key design principles someone should follow when building a harness?
5 principles. 1. Start with verification. It delivers the highest reliability improvement per hour of engineering effort. 2. The model is just one piece of the puzzle. A mediocre model with an excellent harness beats a top-tier model with no harness every time. 3. Measure before you fix. You cannot improve what you do not track. 4. Expect imperfection. AI models are probabilistic, not deterministic. They will fail sometimes for no obvious reason. Build retry logic, fallback options, and escalation paths. 5. Add controls gradually. Don't try to build an H3 system on day 1. Start small, iterate, and layer on more sophistication as you learn what breaks.
So it's the same as building any reliable software system, just adapted for AI's unique challenges.
Exactly. We borrow patterns from distributed systems, like circuit breakers and retries, from MLOps, like evaluation pipelines, and from site reliability engineering, like observability and alerting. but we adapt them for non-deterministic, multi-step, tool-using AI agents. That's what makes harness engineering its own discipline.
So why should someone who's not an AI engineer care about harness engineering?
Because you interact with these systems every single day. ChatGPT has a harness with safety filters and content moderation. GitHub Copilot has a harness that reads your open files and checks code formatting. Every customer service chatbot you've ever used has a harness connecting it to order systems, knowledge bases, and escalation workflows.
And when the harness is bad, we all feel the pain.
Exactly. Bad harnesses mean AI gives wrong medical advice, coding assistants introduce security vulnerabilities, and support bots frustrate customers into leaving. Good harnesses mean AI is reliable enough for hospitals, banks, airlines, and critical infrastructure. The bottom line is simple. A model is a commodity, increasingly interchangeable. The harness is where the reliability, the safety, and the value live.
That's incredibly insightful. Let's recap what we learned today. Harness engineering is the discipline of building reliable infrastructure around AI models. The core formula, agent equals model plus harness. Use guides to direct your agent and sensors to verify its work. Progress from H0 to H3 over time. And never trust the model blindly.
That's right, Jenny. Start small, measure everything, verify every output, and iterate. Thanks for watching SRK MasterStack. If you found this valuable, please like and subscribe. We've got many more deep dives into AI engineering coming your way.